Okay, so we're continuing on with our lesson for 4.2. We haven't talked about this formula yet, though. This is the area of a sector. So the arc length we worked with yesterday was just finding like the length of the pizza crust. But the area of the sector is how big is the piece of pizza. So 1/2 r squared times theta. And once again, the important piece is that theta has to be measuring in radians for you to use this formula. That's just the catch on all of the formulas in trig. Otherwise, you got to use a totally different formula. So instead, we just convert it. So the first question they have for you is we have the circular garden, and there's a radius of 10 feet on this circle. There's little sectors that they've broken it into, and they want to first talk about what area does she use for tomatoes. So area of a sector, remember, we just talked about that as 1/2 times r squared times theta, remembering that your angle has to be in radians. So when I go to look at the tomatoes, I think this is the only section of tomatoes. So using my area of a sector formula, 1/2 times, what's the radius again of the circle? 10. And then this is where kids get a little confused because they forget something very important. Yes, this is 50 degrees, but that's not radians. So instead of like separately converting it to radians, because I know my next step is just to be grabbing my calculator and start typing, I just throw the conversion into the formula. So crank all that into the calculator. These are real life application questions, so answers with pi don't really make a lot of sense. So I want you to type everything in, including the pi. Give me a decimal approximation for this one. And we get, is it like 43.6-ish? And then the most important part is that you give me an appropriate label. So this is area, where the radius was measuring in feet. So the area would be feet squared. Very good. So similar question here. This time we have wildflowers. Just be careful because I was not the first time I keyed this. There are 2 sections of wildflowers here. Both of them are 80 degrees. So rather than just like doubling my final answer, let's just double the angle. So let's call the angle a total of 160 degrees. Very similar setup. 1/2 radius squared times, now this time, like we said, instead of 80 degrees, it's 160 degrees. But don't forget, we need radians. So I'm going to throw the conversion into the formula. And I think we get 139.6 feet squared. And I will be really stinking picky about your labeling, guys. If it's arc length, it needs to be just a distance measure. If it's velocity, it has to be distance over time in the appropriate unit that I asked for. If it's angular velocity, I'm looking for radians per time in the appropriate measure. And if it's, what did I forget? Oh, area of a sector, it's squared units. All right, now this next part of the question goes off of the wildflowers answer. And it says if you have 6 ounces of wildflower seeds will cover 10 square feet, how many ounces does Jaden need? This feels very proportionate to me. So 6 ounces will cover 10 square feet. You don't really need to put the labels down. I just kind of do this because it's easier for me. Thank you. To set up the proportion. Just make sure everything matches. So the question is how many ounces? So he can cover this many square feet. Now, this is kind of a silly answer we end up getting when we cross multiply this proportion. I don't know what we get. I don't have the answer written down for some reason. Can y'all type for me 6 times 139.6? And it's like 83 point something. Was that what it was? 80? Say again, I'm sorry.
837.6.
Did you divide by 10? I was like, wait a minute. There we go. All right. And like Jaden's not going to go to the store and be like, give me 83.76 ounces of seeds. Like, that's weird. This is very demanding of you. So we'll just say about 84 ounces. I don't even know how they sell their seeds. It might be like in packages. So maybe he'll just have to suck it up and buy another package. I don't know. Whoopsies. I need to throw that at you, Brandon. Sorry. All right, moving on. Now we're going to get back to the questions that we were seeing yesterday. These are the ones from Trig that everyone kind of had nightmares about. But remember, I think everyone was here yesterday. So that's good news. Hi, Taylor. I'm say hi, Taylor. She's here on YouTube.
Oh, hi, Taylor.
She'll watch my video. Right, Taylor? All right, one type of wind turbine blade is 27.1 meters long. This is the radius. We'll need that in a minute. The blade is rotating at 28.5 revolutions per minute. So this clue is not angular velocity, but it is a clue about angular velocity, which is where we're going to start the question. So I always start by finding angular velocity with the appropriate labels, and angular velocity has to be measuring in radians per time unit. Now, I am always paranoid about time units because they can switch it on me. They might say things like, I want your answer in per second. They didn't do that in this question, but I'm pretty sure they do that to you on your test next week, so be careful. So we're going to start with the clue of, as it's given, 28.5 revolutions per minute. But I need to do some converting. I need this to say radians per minute. So how many radians are in one revolution? 2 pi radians in one revolution. And then still to this day, many decades later, I still do the cross off your labels and make sure you have the right label thing. That's important. Crank this in the calculator for me. Decimal answer works better. Zinc, you get 179.1. Label here would be radians per minute. So this is your angular velocity in the appropriate labeling. The reason we needed to do that first is because the linear velocity, and when I say angular speed, angular velocity, they're the same thing. The linear speed or the linear velocity, there's a lot of formulas for that one, but we discussed yesterday, the only one you really need to utilize is this guy. It's the radius length times your angular speed. So all you gotta do is make sure you're watching your labels. They don't do anything weird with labels on this question, so good news for us. The radius, if I go back here, was 27.1 meters. I'm going to kind of put my labels underneath like this. And I'm supposed to multiply it by my angular speed, which was, we just found that, 179.1. The label on this guy is radians per minute. And remember, we talked about how the label of radians in the formula ends up kind of canceling out because of the formula, how it works out. So don't worry about radians here. You're going to end up with meters per minute, which is an appropriate type of label for linear speed because it's distance over time. So crank this on the calculator. I have 4852.8 written down. Okay. No, that's not at all what you said. Okay, 48. First hour tried to tell me that, but I couldn't understand what they were saying because they're too quiet. All right, 485. All right, and then probably the difference between us is truncation issue. Like if any of these got rounded off differently, then all right. So this was meters per minute. Labels are very important. You must have them. And that's all I wanted. So those questions for linear speed, angular speed, they kind of always go the same way. Sometimes they straight up give you angular speed, cool. Otherwise you got to do a little converting. Use angular speed to find linear speed every single time. Centrifuge. So Mr. Abruzzo works in a lab at the hospital and he has to work with things, with blood. He talks about these things. I don't want to hear about these things. So he tells me about them and I'm like, that's fascinating, and I tune him out. Probably the same thing he does when I talk about work. So these are the things that spin really fast and the the platelets separate, right? The plasma and whatever. Again, I don't listen. So they're gross because it's blood. So this time they just flat out tell you, here's your angular speed, and it's even in the proper, well, kind of in the proper label. It's radians per second. So that is literally omega. Unfortunately, that's not a very human-friendly answer. They would like you to convert this to revolutions or rotations per minute. So we'll go ahead and start with our radians per second. But we're going to do some converting. In fact, you got to convert two things for me. I need radians to be converted back to rotations or revolutions, and then I need seconds to convert to minutes. So I'll do the radians revolutions one first. Radians need to go away, so there's 2 pi radians in one rotation or one revolution. And then I need seconds to cancel out, seconds to minutes, so there's 60 seconds in 1 minute. And then, like I said, decades later, I still do this thing. Make sure everything cancels. This is like the most satisfying moment of my chemistry career, is crossing off labels and having it work out. Does anyone else find, like, wonder in that? No? It just makes me feel so happy. Because you know you did it right. You're not intrigued by that? Okay. Alright, now you do need to be a little careful about how you're typing this on your calculator. If you literally type in 400 pi times 60 divided by 2 pi, that's fine, but you have to remember that 2 pi is two different things that you're dividing by, so you got to put parentheses around it. You could also notice that the pi's are just going to cancel out. Do you see that? You could even further notice that 2 pi can divide into 400 pi and call it 200. So either way, I need you to type something into the calculator very carefully, and then make sure you have the appropriate label on it. And off zinc, we get 12,000 RPMs. Yeah. You can write out revolutions per minute, but I'm fancy like that. RPM. And that's probably a more human-friendly answer. Like, no one wants to hear about radians. Okay. What is the linear speed? So that's this guy. And it doesn't specify anything about labeling. So if you don't mind, I'm just going to go back and use our original omega. And we're just going to have our answer in per second for a unit. And I don't care, because they didn't seem to care in the problem. So the radius is given to you. The substance is 8 centimeters away from the center. That's fancy talk for radius. So this is in centimeters. And then if I use my angular speed from earlier, 400 pi radians per second, and I crank that in the calculator, I get my real life answer of 10,053.1 centimeters per second. Now, if for some reason boss came back and was like, I need this in, meters per minute. I don't know why you would. That's a really stupid answer. I'd have to go convert it. Maybe miles per hour. Maybe they want miles per hour. What do you think? Okay, she's not here today, but I can hang on to it if they want me to.
Do you want to?
Well, I mean, what changed? Let's see. Taylor, your schedule changed. Oh. Yes. Should I just hang on to it? All right. Cheyenne. Huh?
There's not an escape school pass there.
And like Daniel gets out of school early pass? Yeah. I don't see one.
Because they're supposed to be.
When do I get a you get out of pass? One day I just want to note, like, Mrs. Abruzzo.
Because the stupid kid who blew my eardrum. You have to go get that fixed.
Somebody on your swim team whacked you in the head, I heard. Nate would never.
It's part of one of the games. It's just a game.
No, you wouldn't.
It's a great game.
I'm sure Nate watches this video now.
It hurts.
All right, number 13. This is very a la the question that's on your test, so we should definitely look at 13. Okay, first of all, I don't know if any of these words are things. A flywheel is mounted to an engine crankshaft.
Yes.
Yeah? Okay. Good. Sometimes I read these and I'm like,
It's on the back of your engine between your transmission and your engine. It's the part of the engine that the transmission actually, like, the torque control. I mean, it spins. Yeah, it spins. The torque converter connects to it.
Torque converter?
Yes. It's what's...
I know what torque means.
Okay, so you probably grew up driving a manual transmission, right?
No.
Oh, okay. Are you familiar with manual transmission?
Yeah.
You have to press the clutch in when you're stopped.
This is what I hear,
Or
yeah.
be in neutral. Torque converters make it so you don't have to do that. Torque converter will sit there and just spin. And with the engine and make it to where the...
So it gets to a certain RPM, then it goes to the next whatever.
There's fluid inside it, and there's turbines inside it.
Fluid. Transmission fluid. That's a thing I need to get.
That is a thing. And there's fluid in there, and it's really weird how it works. But basically, like when the transmission's not locked up by the brakes, that fluid will turn the turbines, which also go and turn the transmission. It's very interesting.
It sounds fascinating.
I like cars.
No, I think part of driver's ed should be like car maintenance and just general knowledge, because I am an old lady and I still to this day, when I talk to my mechanic, end the phone call with, I'm sorry, I have to have my father call you and make this question, like make this answer. I don't know. Every time. I am old enough where that shouldn't happen. And I make them call my daddy.
Not even Ryan?
Oh, no. He doesn't. No. We're not car people. He's very smart and will look anything up that he needs to on YouTube, but we don't like to get messed over and spend thousands of dollars, so we just go back to daddy. No.
You at least change the blinker for it, right?
I know that one. No, you don't have that. My what?
Your winter air? The air conditioning system, you have to put the winter air in.
Shut up. Is that why my car smells like dirty socks in the winter? No, that would be the dirty socks in the back seat, actually. That would be what it is. Oh, gross. All right. Crankshaft. It's a thing. All right, so it has a radius of 6 inches. That feels important. Let's highlight that. The engine is running at 2,800 RPM. That is an important clue. Unfortunately, not the clue I need. So what we're going to do is start with that clue, but we're going to get it in the right label. So you can call it rotations or revolutions or whatever. Rotations per minute. And then if I keep reading the question, they want linear velocity, so they want this weird V-Vans looking thing, which is why we're trying to find omega, the angular velocity. But keep reading. In feet per second. So while we're doing some converting here on omega, why don't we go ahead and also convert the minutes to seconds? Because at some point in your math you have to. And there's also another thing we have to convert. Did you catch it? They want feet. And your radius is measuring in inches. Which we got this. But we'll cover that in the next step. Alright, so 2 pi radians for 1 rotation or 1 revolution, whatever. And then 1 minute is 60 seconds. So rotations, gone. Minutes, gone. Got radians per second. Feeling good. Our angular speed is, crank that all in the calculator, 293.2. And that's radians per second. So we're going to use that clue. In addition to that, we need to talk about this radius. 6 inches. True. Not feet. So can I just do that? Or can we just call it 0.5? Y'all know that 6 inches is half a foot, right?
It is.
Yay, English measurement. It's okay. It's a stupid unit of measure. We all know that. All right, 293.2. Just watch your labels. So now we ended up with, this is now measuring in feet, and this is radians per second, which leaves us with a linear speed of feet per second, which is exactly what my teacher wanted. I'm going to get this question right. Type. 146.6 feet per second. This is a little more intensive, I think, than the one on your test. The one on your test, there's only one piece of, sneaky conversion you have to do. So, you'll either have to convert the radius length to something else or the time value to something else. It won't be both of them. That's, too mean. But there is one of those on your test, and I'm sure there's several on your homework, too. Hey, speaking of homework, flip it over. That's 6B. That would be your book work. Thanks, Hoffbauer, you sweetheart. And then also you can do a few questions for me now on worksheet 7, which is the following worksheet. Okay? Could you please find the special right triangles page from yesterday? We're going to discuss special right triangle patterns. This is now added to your homework check. If time allows today, we're also going to start developing the unit circle. It's going to be a hoot. Did you guys have to do a unit circle quiz in honors algebra 2? And trig.
I don't know the units.
Well, you're gonna.
I never learned it.
Well, you're gonna.
I managed to pass trig.
I think the hardest part of the unit circle for me, and most kids, is the radian measure, the fractions. So once you can kind of nail that down, you're good.
I don't know.
So the trick for Abruzzo is color coding the unit circle. Even when I take a test, I bust out a green marker and I do this. I color them so they all kind of visually match up, and that way I know the pi over 3's family should all be green, or,
So
you know, whatever color I choose.
In each
quadrant, yeah.
The first radian that you're measuring in each quarter is exactly 1/4 radian. No, it would be 1/2 the rate of a pi, right? Away from.
Save that talk for after this worksheet, and then we'll talk. I need a visual to see what you're trying to ask me. Because the answer is probably. I don't know what you're asking me. They're broken into just particular families that we use a lot in trig. So the pi over 6 family, the pi over 4 family, and the pi over 3 family. Huh. All right, develop a pattern for the isosceles triangle. So isosceles means that these two legs are the same size. So if it's a general statement, we just got to call them a variable, and most people call them x's, but if you kind of look forward on this worksheet, there's a whole lot of x's on there, so I'm going to avoid using an x as a variable. I'm just going to call them a. They don't seem to like to use a for some reason. And then if you're not sure what the hypotenuse is, because you forgot, you could simply do Pythagorean theorem and solve for the hypotenuse, but anyone remember the quick pattern here? What's the hypotenuse come out to? It's whatever the leg is times the square root of 2. Okay, so special right triangles, this is a 45, 45, 90. These are shortcuts that allow you to come up with the legs of certain pattern triangles without using trig or Pythagorean theorem. They give you beautiful answers that don't, they are irrational, but they're in their proper form once you do some simplification. And these are often things that show up on like extensions of math, like calculus, let's say, or like SAT questions where they want you to go very fast without the use of a calculator. So we're also going to use these to develop the unit circle as well. The hope is that when you guys test the unit circle on Monday, there's very little like thinking you have to do as far as development. But if you're ever in a jam, you might have to quickly develop a piece of it to make sure you have the right family that you're even talking about. Because the worst case scenario is when you're doing the unit circle test, you have like a wrong assumption in the first quadrant, and then it kind of carries through for the rest of the unit circle, which is a problem. Anywho, we'll get back to that. Let's talk about a couple examples here on the front then. So the legs, we know, are the same size. So like if this guy's a 14, that means this guy is also a 14. And then the hypotenuse is whatever the leg is, but then you throw a square root of 2 on the end of it. So that question was really easy because the pattern fit what the triangle looked like. It was beautiful. This one is also nice because the hypotenuse of a 45, 45, 90 is supposed to be leg times the square root of 2. So how big are the legs? Gotta be 7s. So those are very nice because they fit the pattern exactly. But they don't always fit the pattern exactly. So you have to kind of think about what the pattern says. The legs are the same size, so this guy also has to be this funky square root of 10 over 2. But then the hypotenuse is whatever the leg size is times an additional square root of 2. So you're not going to find that answer on the answer key. They're going to want you to simplify this. Smush these together, it becomes the square root of 20 over 2. And then the square root of 20 breaks down into 2 square roots of 5 over 2. And then the 2's cancel. Oops, square root of 5 is the final answer for this hypotenuse over here. So that took me a minute because it didn't fit the pattern. It didn't look like the pattern, so I had to do a little finagling. And then this last one is extra difficult because this definitely doesn't fit the pattern. This hypotenuse is supposed to be in the form of the leg times the square root of 2. So 2 is supposed to look like, you can choose whichever leg you want, I'm just going to go with m, times the square root of 2. So in order to find m, I would have to solve for it in this equation. So I'd divide both sides by square root of 2. And I'd get m equals 2 over square root of 2, but there's not a math teacher on the planet who's happy with that answer. So then they want you to rationalize. And then you get 2 square roots of 2 over 2. And then the 2's will cancel. So 1,000 years later, you find out that m is the square root of 2, which means n is also the square root of 2. And now that I go back and look at that, I'm kind of like, oh, well, yeah, that makes sense. Because if I took square root of 2 and multiplied it by square root of 2, I'd get 2, which was the original hypotenuse. But my brain doesn't really work that way. So I got to set up an equation. All right, 30, 60, 90s. The pattern is It's easy to develop if you remember what a equilateral triangle is. Remember the equilaterals all have angles of 60s, right? So you could split an equilateral triangle into, oops, that was supposed to be split, into two congruent baby triangles, which would be known as our 30, 60, 90. So I'm not going to go through the Pythagorean theorem derivation of this one, but basically they call the leg of the larger triangle like some variable, and then this guy would be half of that, and then after some Pythagorean theorem, you'd find this medium leg, which is really funky, but then no one likes fractions, so then they decided, get rid of the fraction by doubling all of the legs, and this is the pattern they ended up with. So you have a 60-degree angle, you have a 90-degree angle, and you have a 30-degree angle. The little angle, the 30-degree angle, is across from the little leg. We call that leg A, or whatever variable you want to use. The hypotenuse, because it was the original piece of this equilateral, is double the size of A. And then through Pythagorean theorem, they found out that this medium leg, the one that's across from the 60-degree angle, is always whatever the little guy is times a factor of the square root of 3. And it always simplified to that, so that thus became the special right triangle pattern. They are shortcuts. I know kids don't like these, but you have to start viewing them as shortcuts, and then maybe you'll like them a little more. All right, so if they follow the pattern exactly, life is good. So like, for instance, right here, this follows the pattern exactly. This is supposed to be leg times square root of 3, the little leg. So that means my little leg is 7, and then the hypotenuse is double that, so it's 14. Number 8 also follows the pattern exactly. They go ahead and tell you the little leg is 4, which means my hypotenuse would be double that. And then your medium leg, the one across from the 60, is whatever the little guy is, times the square root of 3. So awesome if they fit the pattern. Not awesome when they don't fit the pattern. So let's take a look at our clue here for number 9. The hypotenuse is supposed to be twice as big as the little leg. So that means the little leg is the hypotenuse cut in half. So that's kind of gross. And then the medium leg is whatever the little guy is with a square root of 3 multiplied to it. So that one wasn't too bad. This one gets weird. The medium leg is not supposed to look like a 13. This guy is supposed to be the little guy times the square root of 3. That's what it's supposed to look like. So you can solve this equation for the little leg. So right now, oh boy, here we go. It's 13 over the square root of 3, which no one likes. So then we got to go through and rationalize it. At least this one doesn't have any extra canceling. So the little leg, V, is 13 square root of 3 over 3. The hypotenuse is double whatever that little leg was, and it is a fraction coefficient, which is kind of weird. So to double a fraction, you just multiply the numerator by 2. Don't multiply both numerator and denominator, though, because that would be a factor of 1. So multiplying this guy by 2, you're going to get a 26 square roots of 3 over 3. Whew. Beautiful. Can you imagine doing Pythagorean theorem on that, though? That'd be icky. So there's some questions on your test next week, next Tuesday, the official test, where you have to use your special right triangles to get the accurate rationalized answer. You can't use your trig ratios because it'll just be a funky thing on your calculator that I won't accept. Okay? So on the back, I think it has you have some practice problems there. So you guys are going to work on this for homework. In your homework check. Be really, really good at them, and the answer key is on the back of that, I believe, okay? Alright, let's talk about unit circle fun. Where did I put it? Parts of the unit circle. That sounds promising. Do not write any of this down. You are just talking and walking me through this, and I'm gonna try really hard to draw straight lines. Man, first hour I couldn't draw a straight line to save my life. Apparently this is a very big file. It takes forever to open, and I don't know why. Okay, there are a lot of unit circle songs and tricks for memorization of the components. There's some like arm movements you can do about like the pi over the radian families, like pi over 6, pi over 4. Like, I don't remember what it is because obviously I'm not capable of memorizing things like that. But if you look up on YouTube and just say like unit circle, thousands of songs, tricks, whatever you need for memorization. For most kids, though, it's just, oh, I need to get rid of this. Hold on. For most kids, it's just a matter of recognizing the families. And then for me, I need a little more than just memorizing the families. I need it done in color, too. So how you attack the unit circle is up to you. When you take the test on Monday, it'll be timed. You only get so much time, and there's no calculator. So you're going to have to fill out all of the degree measures, the radian measures, and then the sine and cosine ordered pairs for all of the angles as well. And you'll also have to tell me which trig functions are positive in which quadrant. And then I think there's also a section on the back where I just have you sketch a basic sine graph and a basic cosine graph. Like nothing in detail. Just, we'll talk about this more on Friday, but how cosine starts at the maximum value and does like a horseshoe shape. And sine starts at the origin. And that has to do with the unit circle. So that's why we're kind of putting it all in one little summative. All right, let's talk. For me, when I'm starting off the unit circle, I fill out things that are going to be really, really obvious to me, whether I know trig or not, just so I can make sure I land in the right spot when I'm done. So I fill out what are called the quadrangles. So for degrees, this is 0 degrees. What's this next quadrangle up here? Yeah, that's 90 degrees. This guy is 180. 270, and then you should come back and rotate this to 360. Okay, so then the next one that I like to fill out, it's up to you though, I like to fill out the 45s family because I can divide things in half pretty easily if I get stuck. So like this middle guy here, this is a 45. This is 90, that's the next 45. The next 45 would be 135, 180, adding another 45 would be 225, 270, 315, and then brings you back to 360. So, and you'll notice my color usage is going to be done in families the whole time. Tomorrow we're actually going to sit down and develop an entire unit circle in one sitting. For this one, we're going to do each piece on a different slide, as far as we can get. All right, so next family maybe you want to fill out, totally up to you guys. I like to fill out the 60s next. You don't have to. So like this is 60, and then the next guy would be another 60, so 120. I'm not putting degree symbols on any of these. Oh well. All right, now notice the 60-degree measure marks. It's not like you're counting every single line, so you got to be careful about that. This is the next 60, so 180. This is the next 60. Nope. This is the next 60, so 240. Yes.
That 120 wasn't going to point to the next 60, would it? Be the one after it?
60 plus 60. It's so these are 30-degree chunks, and these little guys are 15s, right? So this is 30 and another 30. Okay. 180. Where are we at? 240. Nope. Here. 240. 300. We look like we're landing in the right spot now. This would be bringing us back to 360. So if I kind of step back and look at where the red pieces are, they should have symmetry to them of some sort, right? They're flowing out in the right part of the quadrant. All right, now the 30 is already here. There's technically a whole bunch of 30s, but they're already labeled, right? 30, 60, 90, 120. Who's this guy? 150, yeah. The reason I saved this piece for last is because whether you measure forward or backwards, they're very easy to fill in, right? And for a lot of kids, they don't have to do the degree measures in families because you're just so familiar with degrees, you don't have to do it. Who's this missing one right here? 330, there we go. Okay, so we got the degrees in, that's nice. This is the part that everyone hates. So again, you want to do this systematically. But remember, on the unit circle test, you're already going to have all of these down because you'll probably do this first. What I don't want to see you guys doing is whole bunch of trying to convert to radians using the pi over 180 conversion. You would only do that if you're like super stuck. You're not going to have time to do that. So we got 0 radians. I'm going to do the same method. I'm going to do the quadrangles first. Do you remember who's up here in radians? Pi over 2. And this is pi. And this is 3 pi over 2. And then coming back here would be 2 pi. Here's what I do. I count by half pies. 0, 1/2 pi, 2 halves pi, 3 halves pi, 4 halves pi. Okay? This involves fractions. That's why kids don't like pies. All right. Next, I think the 45s or the pi over 4 family would be best. If you took pi over 2 and cut it in half, you're with pi over 4 family. So this guy is 1 pi over 4, 2 pi over 4. Who's this? 3 pi over 4, 4 pi over 4, 5 pi over 4. This guy would have been 6 pi over 4. So this next one is 7 pi over 4, which brings us back to 8 pi over 4. Is that where 2 pi is? Yes, okay. So in a perfect world, I could draw a straight line and these would all be perfectly done. You know what I should do? Is use my highlighter because it'll adjust it and make it a line. Oh well. Now, pretend those are straight and kind of step back and look at it. Is the symmetry there that I'm looking for? Okay. I do pi over 6s last because they mess with me. I'm going to do the next group, which is pi over 3. Pi over 3. Now, if you have a hard time remembering that, this guy is 1 pi over 6, so the next 30-degree mark would be 2 pi over 6, better known as pi over 3. All right, so now I look for all my symmetry. So like this piece and that piece. Oh, I'm doing the wrong one. There we go. The good news is when you start to draw these lines, you're going to notice if it doesn't look right, even if you draw scribbly like me. All right, count with pi over 3s with me, guys. Ready? 1 pi over 3. 2 pi over 3. Now, this is what messes with kids. This one, which I didn't mark, is 3 pi over 3. Right? 3 pi over 3 is pi. Okay, keep counting. 4 pi over 3. 5 pi over 3. And then again, this one, which we're not marking, is 6 pi over 3. You can. But here's what I want you to remember. When you're doing this test, you're already going to have these colors down. So as you're like measuring and labeling, I screwed up my colors, whoopsies. You're going to be able to connect like, oh, this matches with this. This matches with that.
Excuse the interruption. Is Daniel Lamb in there?
Yes, he is.
Will you have him come to student services? I believe he's leaving.
Okay.
Thank you.
There you go, Daniel. All right, now for the one that nobody likes, or at least I don't like. I don't know how you all feel about it. Oops, wrong color. 5 over 6 family. Now, what bothers kids is they see where they're supposed to be, but pi over 6 is a lot more than just what I'm coloring in red here. What I need to remember, though, is everything that I just colored in red needs to have an over 6 component to it. So it's up to you. If you'd like to count every little 30-degree chunk, you can. You can go 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6. Totally fine. What I do is I just back up from the nearest quadrangle. So I know this is really like 6 pi over 6. So if I take away one of those, this is 5 pi over 6. And then if I add one of those, I get 7 pi over 6. But some kids don't like doing that. They're not comfortable with the fraction, so they just need to count every time. The trick with counting, though, is that you have to make sure you're counting the right pieces. So like this is a 30-degree mark, this is a 30-degree mark, this is a 30-degree mark. That's the trouble. All right, 7 pi over 6. So over here, the last one I got to fill out, remember this is like a 12 pi over 6. So if I back one up, it's 11 pi over 6. That's why I leave those guys for last, because I feel like they have the most opportunity for screw-ups. And you can recognize, like, there's no pi over 8s on the unit circle. So it's not like you're going to throw a pi over 8 or, like, pi over 5 doesn't show up on the unit circle. So, you know, there's only so many things for you to choose from. So if you've already used a 2 pi over 3 and you think you're going to write another one down, something's wrong, and you're going to be able to fix it. All right, we'll pick up here tomorrow with the rest of the unit circle, because the next thing we got to talk about is all those special right triangle patterns and how they result in sine and cosine values, or x and y values, which I know no one likes this part, but this is actually the easiest part of the unit circle. All right.